So for waves, we can measure rates of energy flow, which waves often carry in terms of power and intensity. If you remember, power, we already defined, is energy or work per time, right? Intensity is, so this is power, right? This is intensity, is power over area. And so the sun gives off energy per time, right? The sun is constantly radiating energy outward, and the rate at which it leaves the sun is something like 4 times 10 to the 26th watts, or something like that. It's just joules per second, right, leaving the sun. You can also talk about the energy that reaches the earth per second. The sun is constantly pouring energy onto the earth through its radiation. And so the power delivered is the energy per time. The intensity is the power per area. So how big an area is that power spread out over? Right? If I take a very intense light bulb and I make a very intense light, and I make a spot of light that big, and then I drag my flashlight further out, and now the same light is producing a spot this big because the flashlight is farther away, then it's less intense here than it is here, because they both have the same power, but this area is smaller than this area, right? And so let me see if I can do an example of that. So so the intensity due to sunlight is 700 watts per square meter. That's the average intensity hitting the earth. It's power per area, so it's watts per square meter, and it's 700 watts per square meter. That's the average amount of sunlight that reaches the earth, right? And so we can ask how much energy is absorbed by a 0.5 meter by 0.5 meter solar panel in 4 hours. Right? So what they're asking here is energy, so they're asking us for this thing, right? But they're giving us the intensity, which is this, right? That's our intensity, and our area is this, right? The area is 0.5 meters by 0.5 meters, which is 0.25 meters squared. And so we can use this formula and say, look, the power is just the intensity times the area, which is 700 watts per square meter times 0.25 meters squared, right? And so that's 175. A quarter of that is 175 watts, right? And so that's the power that's getting. So if you have a 0.5 meters squared solar panel, maybe about the size of this whiteboard here, and the sun's shining on it all day, it averages about 175 watts. So enough to run maybe a PC or something like that, your laptop, right? And so usually if you want to you run your house, you have much bigger solar panels covering your whole roof maybe. And then it says it wants the energy, right? Well, the energy is the power times the time, which is 175 watts times 4 hours, which is 700 watt hours, or 0.75 kilowatt hours. If we wanted to, we could make that in joules, right? By writing 700 watt hours times 3,600 seconds per hour. And that would be, if I can find a calculator that'll do that quickly. 2 2.5 times 10 to the 6th joules. So that would be the energy. So let's talk about human hearing. Right? Humans can hear from about 20 hertz to about 20,000 hertz. This is way off the top of the piano. These are just really extremes. Most people can't hear this. I certainly can't. Or this probably, but somewhere in the middle. But the younger you are and the healthier your ears are, the more likely you are to hear those inside that range. So humans can hear over that range. And so if we want to find the corresponding wavelengths, we can say, well, look, the speed of the wave, we'll just pick 340 meters per second just to get a rounder number than 344 at room temperature. And we'll look and say, look, lambda 1 F1 is equal to the speed of the wave, and so lambda 1 is equal to the speed of the wave over F1, which is 340 meters per second over 20 hertz, which is 1 over seconds, and so that's 17 meters. And so that's the wavelength of the low end of the lower frequency. It's a large wavelength and a small frequency, right? And I can say lambda 2 F2 is equal to the same velocity, right? All waves travel with the same velocity, and so lambda 2 is equal to the velocity of the wave, or F2, which is 340 meters per second over 20,000 hertz, which is just 1,000 times smaller than that, and so it's 0.017 meters, or 1.7 centimeters. And so those are the short wavelengths, and those are the long wavelengths. The interesting thing about sound that we hear are these are sounds that are comparable to the size of typical things in our lives, right? Windows and doorways and stuff like that are somewhere in this range. And light has waves have interesting properties when the things they bump into are around the same size as their wavelength. And so that's one of the reasons hearing is interesting and effective at the sound frequencies that we hear. So we're going to talk a little bit here about loudness. So the loudness of a sound is really its intensity. It's related to the amplitude of the wave. And so, you would represent maybe a quiet wave this way, and maybe a loud one this way. The representation of them would be like that. So this would be quiet, and this would be loud. So the loudness is really proportional to the pressure changes in the along the wave, but we can just it's actually proportional to the square of the amplitude, but humans don't quite hear in proportion to intensity, and so there's something called the decibel scale that determines that's a representation of how we hear. And so for this we use So the sound level is represented by the letter beta, the Greek letter beta, and it's 10 decibels. The sound levels are measured in decibels times the log, and this is the base 10 of the intensity over what we call I0. So if I have a sound with intensity I, the sound level for it will be this, and this is a representation sort of what we hear. This isn't a law or anything, this is just a definition. We call the sound level 10 decibels times the log of the ratio of the intensity that we're looking at over this quantity called I0. I0 I0 is the threshold intensity of human hearing. It's the lowest intensity your ear will detect, and it's given to be 10 to the minus 12th watts per square meter. That's a trillionth of a watt spread out over a square meter. So you can imagine how sensitive the ear is, that it takes something, that it can detect something that's got that small an intensity, right? And so so that's what goes in here. The intensity that you're asking about goes in here, and then the rest of this stuff is just math, right? And so we can do a few of these things. We can say, well, what is the sound level? Sorry. So this is our formula. Beta is 10 decibels times the log of I over I0, right? But we're saying the intensity of the sound is the same thing as I0. In other words, what's the sound level for the lowest threshold we can hear? Well, that's just 10 decibels times the log base 10 of I0 over I0, which is equal to 10 decibels times the log of 1. But the log of 1 is just 0. And so that's just equal to 0, because 10 decibels times 0 is 0. And so on the decibel scale, the lowest sound level you can hear is 0. Okay. All right. I'm going to make a little aside here and talk a little bit about logarithms here for a minute.